@Hookin1 made an interesting video where he connected 4 light bulbs in series and shorted out the last light bulb. And then when you pull out the lead that's shorting it out, it takes a long time for that last light bulb to come on. And he posed the question, why does it take such a long time? Let's watch it again at half speed. We can see the other light bulbs get dimmer as it gets brighter. And let's check that all the light bulbs turn on quickly when we don't have the short there. And yes, they turn on pretty quickly. To understand what's going on, I'm going to use a data logger, which is going to measure the potential difference or voltage across these 3 bulbs, the potential difference across the 4th bulb, and because it's a series circuit, the current in the circuit, which is the same everywhere. And I'm going to do this first of all for when I switch on all 4 bulbs at the same time without the shorting wire. So let's see what graph we get. You can see that, as you'd expect, the 3 bulbs get a much larger share of the potential difference than the 4th bulb on its own. But what's interesting is if we look at the current here, which is in the green, that initially the current is higher and then it falls down to a steady lower value. And that's because when the bulbs are switched on, they're cold and they have a lower resistance, and therefore we get a bigger current. But as they warm up, the resistance of the filaments increases because of the positive ions vibrating more, and that means that the resistance goes up, and therefore the current falls. Now let's try the same data logging, but when I've got the shorting wire across the 4th bulb and what happens when I pull that wire out. Before you pull the shorting wire out, all of the potential difference is across the 3 bulbs and none of it is across the 4th bulb. At the moment when you pull the shorting wire out, the resistance of the 4th bulb is small. Remember that it's cold at that point, so the positive ions aren't vibrating very much, which is why the resistance is small. And so the 4th bulb only gets a small share of the potential difference. And because the potential difference in a series circuit must add up to the power supply, the potential difference across the 3 bulbs goes down that small amount. You can also notice that the current goes down a little bit because the total resistance has gone up. Now we can understand why the 4th bulb takes a long time to start glowing if we think about the power equation in an electrical circuit, which says the power transferred is going to equal the current times the potential difference. And at the beginning, the potential difference across the 4th bulb is small, and so the power being transferred to it will also be small. However, as the filament of the 4th bulb heats up, it increases its resistance, so it increases its share of the potential difference. So the potential difference across that 4th bulb goes up, and correspondingly the potential difference across the other 3 bulbs goes down. As that happens, it means more power is being transferred to the 4th bulb and it starts to glow brighter as it's hotter, and you can see that as the total resistance of the circuit is gradually increasing, the current in the circuit goes down until it reaches a steady value. Let's finish by watching that 4th light bulb come on very slowly when that shorting lead is removed. Thanks to Dan for sharing this great thinking problem, which you can discuss with your students.